All right, I think we can get started. So thanks a lot everyone for joining this webinar. We are very excited for you to bring this topic today, which is using scientific machine learning for battery degradation modeling. As always, we have me, Dr. Rajat and Dr. Shridath. But today we also have with us Sharv, who will be covering about the battery degradation project which he has worked on. This is an incredible project which he completed from start to end, and we also got it accepted to the MIT undergraduate research conference. So the way we have sorry, the way we have structured this presentation is that for the first half of this presentation, we'll be going through the concepts of scientific machine learning, and then Sharv will take you through the entire workflow of the project, how he started the project, how he took it to completion, and then to the publication level. So let's get started. We are recording today's lecture, and we'll be sharing the recording with all of you who are present in the call, as is mentioned on the chat. If you have any doubts or any questions as this lecture proceeds, please feel free to ask it in the chat so that we can clarify all the doubts which you might be having. So today's agenda is as follows. As we always start these scientific machine learning webinars, we'll get started with my story and why we are conducting this webinar in the first place. Then we'll move to the next agenda point, which is the problems with traditional machine learning approaches and why should you even learn about scientific machine learning. Then we will have a section on intro to scientific ML. These three sections are really needed for you to understand the project part which is coming, and that's the battery modeling project which Sharv will deep dive into. But for you to really appreciate that project, you need to understand what exactly is scientific machine learning, what are the applications, etc. And as Sridhar mentioned on the chat, Sharv is a high schooler and he has done this incredible work. So we thought bringing him to the webinar will really inspire all of you to start projects in scientific machine learning and how impactful this field really is. Okay, so let's get started with my story. Um, Before that, actually, I have a form which I want all of you to fill so that we have an understanding of your domains really and how much experience you have with machine learning. So I'll just share this form in the chat. And as I am going through the slides, please fill this form. I'll come to a particular slide, and at that slide, I'll look at the results of this Google form. Okay, so first, let me give you a bit of introduction and background about my story. I graduated with a BTech in mechanical engineering from IIT Madras in 2017. And at that time, I had no background in computer science. I had not formally studied machine learning at all. Then I joined MIT for a PhD. And when I joined, I wanted to be a professor in mechanical engineering. I entered MIT with that goal. So the problem started happening after the second year of my PhD. I went to a career fair at MIT, and there I was interacting with a number of companies who had come to offer jobs. And what I saw there really changed my whole perspective. So I saw that the number of jobs available for mechanical engineering were really reducing a lot. In fact, there were a lot of jobs, most of the jobs for ML expertise, artificial intelligence expertise. So I felt really left out. I felt that I have no experience in machine learning and I should really upskill myself if I want to prepare for the job market. So I started losing interest in mechanical engineering. And at this point, I also had thoughts of quitting MIT. So the whole dream of becoming a professor, which I had joined MIT for, really came crashing down. And at one point, I was literally booking flight tickets back from Boston to India. I was lucky enough to find a research group at MIT, which introduced me to this field of scientific machine learning. And when I joined this group, my whole life or the PhD life took a U-turn. Until that time, I had not studied machine learning. What happened in the next 3 years was that I studied machine learning from scratch. Not just that, I published machine learning papers, which today have 400 plus citations. And I also defended my machine learning PhD thesis at MIT. And all of this happened within a period of 3 years. Um, these are some of the papers which I published at the end of my PhD. Here are some papers which are scientific machine learning applied to epidemiology. And I also worked with a number of startups and governmental agencies to do this research work. Not just research, but at the end of my PhD, I received machine learning interviews, job offers with multiple companies. Now, your question would be that how did I make this possible? How did I switch to machine learning from mechanical engineering background? And how did I build my profile with respect to research as well as jobs? So remember, when I show these companies, I did not reach out to them. They reached out to me looking at my profile. And the field of scientific machine learning really helped me to make this transition. And today, in the first half, I'm going to share with you how I learned about scientific ML and why I think that traditional ML is not the best way for engineers to go forward. Before that, let's see the form which has been filled by around 41 people so far. And we can see that all the students in this call have a wide range of background. We have 9 mechanical engineers, 3 electrical engineers, we have 4 civil engineers, 12 CS engineers. Awesome. So we have a big split over here. To all of you present in this call today from all of these different types of fields, please keep in mind that scientific machine learning is a field in which all of you can really transition to. So the journey which I'm going to explain to you right now is equally applicable to all fields. And I can see that around 50 to 60% of people in this call are complete beginners in ML, just like I was before I switched to machine learning. And about, I would say, the remaining half are split between basic, intermediate, and advanced proficiency in machine learning. Okay, so good to see this student background. Now, let's move to the next part. The first myth which I want to break for everyone in this call is that is ML only meant for CA students? So I used to think that machine learning is only meant for CA students. And remember, I had no background in formal CS. I had not taken data structures or algorithm courses. I had not taken any CS course in undergraduate, in fact. I was just core mechanical engineer. So the first myth which I want to break for all of you here is that no matter which field you belong to, whether you belong to mechanical, electrical, CS, biological, chemical, of course you can transition to machine learning. If you are in CS, that's well and good. You can definitely transition to machine learning, but people belonging to all these other fields, since I switched from mechanical to ML, it's fully possible for you also. And why am I showing this slide to you right now is because when I was at MIT, one senior convinced me that instead of just leaving MIT, you can also switch to machine learning. That gave me the belief system. So I'm hoping that this webinar serves as that kind of a belief system for all of you in this call. Okay, so after coming back to India from the US after I finished my PhD, I really started thinking about how was I able to switch to machine learning that quick. So I finally understood 3 reasons behind this transition. The first reason is that I now strongly believe that the way traditional machine learning is taught is not correct for engineers. So that's why I studied a new field of scientific ML. I stumbled upon this field accidentally, but now I realize that due to that accident, it really was a blessing for me. The second thing is that I had the belief that I can make this transition. So you need someone to give you that belief. Only if you have the belief, then the transition might be possible. The third thing, which is extremely important, is that what I see many students do nowadays is that they do quick Kaggle projects or they do quick GitHub projects and they add that project to their profile, right? Now, think about this. Every single student is doing the same thing right now. So, how do you distinguish your profile from others? The answer to this is that you should really focus on the research. And when we come to the project done by Sharv in the later part, you will see that there is a strong emphasis on the research. You should not just do quick projects and add them to your resume. Projects have some value, but converting those projects into research publications carries much more value. So I did not stop by doing quick projects. In fact, I did not update my resume till the last year of my PhD. I only updated my resume after I had these publications. So these are the 3 reasons which helped me transition to machine learning, right? Okay, so now let's come to the part 2 of the presentation, which is uh, here I mentioned that the way traditional machine learning is not correct for engineers. Let me expand a bit on this. So what are the problems with traditional machine learning? So I want all of you to go to this link, MIT 6.86. I'll also type this in the chat right now. This is a free machine learning course by MIT, and the slides are available. The lecture notes are fully available. So can you just click on this course syllabus here and go to the PDF which they have? It's publicly available. So if you look at the way this course proceeds is that they first start with linear classifiers, then they go to non-linear classifiers, then we have neural networks, unsupervised learning, reinforcement learning. Okay. It's fine if you don't know these terms. What I want to illustrate to you is the kind of projects which you do as part of these courses. So if you look at the first project, it's essentially automatic review analyzer. If you look at the second project, it's digit recognition. In fact, I've collected some of these projects over here. The first project is automatic review analyzer. The second project is digit recognition. The third project is Netflix movie recommendation. There is another project on sentiment analysis. Most of the introductory machine learning courses which you will do these projects. Now, doing these projects is fine, but most of the students just stop at these projects. Do you see the problem with these projects for engineers? Imagine that you are one of the 10 mechanical engineers in this call. How can doing a project on digit recognition or automatic movie analyzer, how is this related to your domain? These projects are completely unrelated to the field of mechanical engineering. Imagine if you are from biological science, chemical engineering, physics, ocean engineering, finance, aerospace, all of these fields. How does a project on review analyzer, digit recognition, Netflix movie relate to your main field? It does not relate to your main field at all. That's one of the major issues with these projects. These projects don't show you how to combine machine learning with domain specific knowledge. Ideally, you should be taught how to take your main field and apply machine learning methods to the problems in your field. Only then we will get impactful projects which are related to your field. You have already spent so much time in all these domains which you have filled this form. It does not make sense for you to do ML projects in completely random topics. You should take topics in your main field. Let's say if you do a project integrating machine learning with fluid dynamics, that's an awesome project, right? Electrical engineering, if you do a project integrating ML with electrical engineering, that is a very cool project. The second problem with these projects is that, and that's a very big problem, we cannot publish research papers with these projects. Why? Because these are toy projects. They are not serious projects. Literally anyone in the world right now can just take the code for these projects, run it on their machine in 2 hours, and put it on their resume. These are not serious projects. Doing these projects and adding it to the resume will not qualify you as a serious machine learning candidate. That's the second drawback with these toy projects. The third main drawback, as I already mentioned, is that without leaving your main field, you should be taught how to integrate machine learning in your main field. That's the main thing which we should really focus on. So now let's look at some of these projects. How to use machine learning to model COVID-19 infections in all the regions of the world. If you are a CS engineer like I was, this is a cool project to add, right? Because all the other CS engineers won't have such machine learning projects. If you are, let's say, a chemical engineer, what if you do a project to recover chemical reaction equation from the data alone? So now this is a machine learning project which integrates your field of chemical engineering with ML. Then let's say if you are a physicist and you do a project which uses machine learning to predict black hole dynamics. This is another cool project which is at the intersection of machine learning and physics. And let me see how many physics students are there in this call, right? Okay, so two students. So to the two students in this call, you might be able to relate to this. Now, what if students who are in economics or data scientists or finance, right? What if you use machine learning to predict economic market forces like supply and demand? Wouldn't these projects be directly related to your main field, and wouldn't you be more interested in these projects? Um, Someone has asked about computer science students, right? Great question. So when I transitioned from mechanical to CS at MIT, this was the project which I did. This one, using machine learning to model COVID-19 infections. Now, all the other computer science students in your batch, they will have projects, but none of them will use machine learning to solve some impactful problem. As a CS student, if you use machine learning to solve epidemiology problems, that would be a really strong addition to your profile. In fact, when I graduated in my last year, Meta Amazon and Julia Computing reached out to me because of this project. And at that time, I'd switched to being a CS engineer. And I believe they reached out to me because of these publications. Similarly, whichever field you belong to in this call, let's say if you are a biology engineer or a chemical engineer, why don't we do projects at the intersection of ML and biochemistry? And I'm not just showing these snippets, which are random snippets right now. All of these projects are actually done by people and they are published papers in the field of scientific machine learning. All of these projects which I'm showing you are papers in the field of scientific ML to show you that indeed these projects are possible and we can convert these projects into research publications. Now, there are, I'm sure, mechanical engineers, fluid mechanics people, and climate people in this call. How many of you know about the Navier-Stokes equation? Can you just type yes in the chat if you have heard of a Navier-Stokes equation or uh, any fluid flow equation? Great, right? See, all of you have heard about Navier-Stokes equation. So what if you use machine learning to integrate it with the Navier-Stokes equation to analyze fluid mechanics and climate problems? Wouldn't that be an absolutely impactful problem for all of you to solve? So these are the kind of projects which you should be doing. And by the way, if you do these projects, not many people would have done it. So you can take it to completion. So Sharv did a project in battery modeling, right? The project which he has done is so unique that no one else literally in the whole world has worked on that project. So that's why he could publish it at MIT's conference. If someone else was already working on the project is not unique anymore. The advantage with scientific ML is that if you do a good job on the project, it's easy to take it to publication and have an advantage in your profile. So the main point is that if you learn to do these scientific machine learning projects on your own, you will have a very strong foundation in machine learning and you will have a firm knowledge of how machine learning can be integrated in your main field. That's number one. Number two is that you can do independent research in your field of study and publish papers in top tier journals. Once you have papers, then you can add these on your CV and they won't be toy projects anymore. They will actually be serious projects because job interviewers, admission committee members, they really respect research projects and research publications a lot, much more than toy projects. You can even do many things like you can reach out to professors in the field of scientific machine learning. So since I was at MIT working in this field, I know that there are many professors at MIT, Stanford, all these top universities who are looking for bright students who are knowledgeable in the field of SciML. So if you have done some initial projects and have publications, you can reach out to these professors and you can start projects with these professors at these top universities. Doing scientific ML projects can also improve your grad school profile tremendously, as we have personally seen from the students enrolled in our scientific ML bootcamp. Now we will come to the next part, which is introduction to scientific machine learning. So Dr. Rajat is going to cover this part. After this part, we will move to Sharv's project. So please pay close attention to this part because if you appreciate what is scientific ML, you will really be able to appreciate the project which is coming after that. Okay, hello everyone. Let's move to the next part of the presentation, which is explanation of the field of SciML. So till now, all of you have heard that SciML is a field which allows you to preserve your core knowledge, your domain expertise, and apply machine learning on top of it. The main question which might be there, it's quite natural, is how do we exactly do that? And I remember 4 years back when I was in the middle of my PhD, there was a heated debate in my lab on which should be the directions our lab should take. So this was at Purdue University. And so my professor was of the thought that ML basically can be used to solve physical problems. And there were some other professors who had a counter to that, saying that yes, ML is useful, but it's useful for quantitative data. It's not useful for real life physics where scientists have already developed these equations. And up until that, there was not a real proof that machine learning can actually help us in real life physics problems. So if we consider the domain of fluid mechanics, for example, there is a famous Navier-Stokes equations which actually govern all the fluids, the motion of air, any types of gas,
and all the liquids that we see around us. So there was a camp of people who were skeptics. They were saying that ML is good for these data related tasks, but for more traditional projects where intuition is required, ML cannot really grasp the physical intuition of things. So there is not a real point in applying ML to these kind of tasks. And there was a second camp of people who was actually advocating for application of machine learning to physical sciences as well. And at that time, that was just the start of the field. And eventually now we have reached a point where scientists are pretty much convinced that machine learning is not just useful for solving toy projects, which Raj was mentioning, but it can be used to solve these real life problems as well. And scientific machine learning offers you one of the ways to do that. How do we do that exactly is we combine the branch of machine learning with the domain knowledge. Now, where exactly the domain knowledge comes from? So this is where it gets really interesting. Let's say we are looking at any physical phenomena. Let's say we are looking at the motion of a pendulum, right? So people must have written a governing equation which tells you how the angle of the pendulum is going to vary with time. So let's say the governing equation is a second order differential equation. Now, let's say you collect the data using measurements, and you find that the data that you have collected is not matching the governing equation exactly. There is some discrepancy. So the objective is that can you now use machine learning to basically keep the core equation the same, but augment that core equation with a neural network, and then train that neural network so that it matches the data that you have collected. What are you doing in this process? We are basically preserving the main scientific structure of the pendulum movement, which is the governing equation, which scientists have already found out through years of research. And then we are simply augmenting that basic governing equation with a neural network term. And then we are applying the techniques of traditional ML to train the neural network to match the data. So if you look at this in the format of a puzzle, right, there are two things that you need to basically complete the puzzle. The first part of the puzzle is the scientific equation itself, the governing equation of the problem. The second part of the puzzle is the data, and you combine both these things together, and then you get a scientific machine learning model. And traditional ML is typically a black box. It is not interpretable. I can fit a neural network to a data, but I don't know what's exactly happening, which was the biggest criticism when you tried to use a neural network. You use a lot of layers, that's fine, but what what is the scientific form of the neural network? That's not very clear. In other words, can we replace the neural network in terms of an equation? So that was not possible before. And with scientific ML, we can now combine the power of neural networks with the interpretability of scientific structures. And the reason why we were saying that it's really applicable to all of these fields is that, let's say you are interested in one field. Let's say chemical engineering, and you're analyzing a particular problem. Any problem that we are analyzing has to have an equation that governs that problem. And that can be a very simple equation, which can be the starting point of your project. Now, what you see is that, let's say when you collect the data, the equation does not match the data. There is some discrepancy. And then you try to augment that equation with a neural network term so that the collected equation, the final equation matches the data. And then there is a next step to it, which is uncovering the symbolic form of the neural network itself. We will not be focusing on that today. That is the next step in the field of scientific machine learning, where we don't just train the neural network, but we use something called symbolic regression to identify the missing terms itself. But that is optional. That's not something we do in all the projects that we study. So overall, this is the brief gist of what is the field of scientific machine learning and why is it applicable to all the fields. It's not exactly rocket science, right? Basically, all of these fields are having some sorts of governing equation. And all we are doing is that we are constructing an equation by augmenting these governing equations so that it matches the data that we have collected. Sometimes the data can be synthetic data as well if you have not collected real life data. So this is a more traditional definition of machine learning, which was written by Dr. Chris Rakaukas. He was the advisor of Dr. Raj at MIT. So Chris says that SciML is a model-based data efficient machine learning. At the bottom, you can see we have a figure which combines data and models, and then both of these components are mixed together to get good predictions at the end of it. And this field is really uh, uh, booming right now. A lot of research groups are opening up new positions in the field of SciML. I recently saw a job post on LinkedIn where there was a very famous research group who had opened up positions on climate modeling using scientific machine learning. Basically, can we preserve the main physics of climate models, but make the models better by incorporating neural networks and then training them to match the data that we have collected? Okay, so at the heart of scientific machine learning, at the heart of scientific structure, always lies an ODE or a PDE. ODE is a short form for ordinary differential equations, and PDE is a short form for partial differential equations. You see ODEs all around you. Whichever phenomena you take, there is always an ODE present. Let's say I'm sitting in front of my laptop right now. I move the laptop with my hand, right? The laptop moves. What's the ODE related to that? I am applying a force and there is a movement. So the ODE is force equal to mass into acceleration, where acceleration can be replaced as d square x by dt square, where x is the variable, x variable, and t is the independent variable, which is time. So this is the second equation which is written at the bottom of the screen. Why is this an ordinary differential equation? Because there is a single variable that is varying with time. We'll look at partial differential equations also shortly. But this is an example of a second order ordinary differential equations. The example of pendulum that we took, that is also an example of a second order ordinary differential equation. I'm sure all of you must have studied some or the other ODs in your engineering, irrespective of the branch that you're working in. Even if you are in CS, we have worked with a lot of CS students, and whichever project they choose, sometimes they initially tell us that I've forgotten ODs and PDs completely. I did it way back. So how will I be able to tackle this problem? So the thing that you need to understand is that getting the differential equation is just maybe 10% or 15% of the overall project. Once you get the differential equations, that's it. That is all the scientific structure we are going to need. The rest of the knowledge is the expertise that you have in training the machine learning model itself so that it matches well with data. So your maximum time is going to be spent in the machine learning part itself. This part can be taken from literature. You need some amount of understanding also, but not that much. Then these are some other two equations in physics, in biology and ecology, where you typically see these ordinary differential equations. Then what are partial differential equations? Partial differential equations are basically equations like these. Let's say we consider the heat equation. So we have an operator which is called as the del operator. Now, why is this a partial differential equation? Because there are multiple independent variables. We have time here as well as we have x and y. Students who have seen this operator before, you can just type in the chat what is this operator, this inverted triangle over here. So does anyone know about this? Okay, yeah, gradient. It's also called as the del operator. And if you expand this, it means that dou square u by dou x square plus dou square u by dou y square, which means you are taking a spatial derivative of the variable u in both x and y directions. But you can see that there are three independent variables, t, x, and y. That's the reason it becomes a partial differential equation. The basic message behind showing these equations is that whichever physical problem that you are considering, whichever field you are looking at, every field can be represented by either an ODE or a set of ODEs or a partial differential equation. And this is where you start analyzing your problem. Okay, so now we will look at this theorem, which is called as the universal approximation theorem. The universal approximation theorem basically states that neural networks have the potential to learn and represent any function that is out there. Okay, so let's consider a hypothetical problem where you have a data, right? And then you have a scientific structure, which is the initial equation. Let's call it G. And let's say this equation is not matching with the data. So what you do is that you augment this equation. Let's say we call it G plus NN, right? So what do we want? So this is a very simplistic equation, but I want G plus NN to match the data, which I'm calling as D. And I'm training the neural network so that G plus NN is as close to D as possible. Now you can see that there is an underlying assumption here. What if the neural network is never able to approximate the data? How come I'm so confident that if I train well enough, the neural network will be able to guess the underlying function so that if you add it with the governing function, it will match the data. It turns out that this is not an assumption, but there is a theorem which actually proves that neural networks have the potential to learn and represent a vast range of functions. But the catch here is that the training might be difficult in case the function is very complicated to learn. And this is where the expertise, or I would not say expertise, I would say the tenacity of the student or the researcher who is working on the problem lies in. If you are tenacious enough, you will be able to train the neural network so that it matches with the data. And this is what is the meaning of the universal approximation theorem. It basically states that you can approximate any function with a neural network term. And now keeping this theorem in mind, we can now mix neural network with differential equations, and then that becomes the total differential equation, which is often called as the universal differential equation, or UDEs. So you might have heard this term for the first time, which is universal differential equations, or UDEs. It is different from ordinary differential equations. Why? Because ODEs do not have neural networks. So it's a combination of ODEs or PDEs plus neural networks. That's why the combined term, it's called as universal differential equations. Sharv will be also talking about how he used these sort of equations in a very real life problem as well. So you will get an application of universal differential equations in practice when we actually teach that as a part of the project discussion. Basically, there are three pillars of scientific machine learning. Along with universal differential equations, there is also something called as neural ODEs. Why they are different from UDEs? It's because in neural ODEs, basically we replace the entire structure with a neural network. So here some core part of the equation does go missing. Some essential physics are missing here, but the entire network the entire equation is represented by a neural network. And the third one is called physics informed neural networks. There are some intersections between pins and UDEs, but conceptually pins are a bit different than universal differential equations. In today's lecture, we are going to be concerned with UDEs and neural ODEs, and we are going to look at an application of this in the battery degradation problem as well. Okay, so just to summarize, UDEs are a class of machine learning models that use the framework of ODEs for deep learning. And they are used to recover missing physics in a scientific system by recovering parts of the system with a function approximator like a neural network. Some of you might be thinking, how do we recover the missing physics? I have not explained that yet, right? There is a way to recover the missing physics from the neural network itself, which is called as symbolic regression, which is the next step in scientific machine learning. And addition of both of this actually completes the picture. Okay, so this is just an example of a problem which Dr. Raj worked on. It's the SIR problem, which is a model which is typically used for um, S stands for susceptible, I stands for infected, and R stands for recovered. This was a model he employed during the COVID-19 pandemic to understand how did these different sections of population grew with time. And here, I just want you to focus on these blue terms, which we have shown in a circle. So it says replace unknown portion. What does that mean? It means that this portion we are going to replace by a neural network. So there will be two neural networks here to replace the two blue circles. And these neural networks will then be trained so that we are matching the data. This is a very practical example of a universal differential equation because you can see that there is an ODE already here. So S dash at the top represents derivative of S with respect to time. So ds by dt equal to, there is a function and there is a neural network within the function itself. So you can see that there is a scientific structure and there is a neural network added in the structure itself. And both the things are combined uh, in the entire equation, and that's why it is an example of a universal differential equation or a UDE. Okay, so I hope you have got an understanding of what's the field of scientific machine learning and why it holds a lot of promise, why it is applicable to any number of fields that we have discussed before. What is the meaning of universal differential equations and what is the entire premise of scientific machine learning itself? Now I will stop sharing my screen, and in the next section, I will ask Sharv to share his screen and take you through his project.
Thank you so much, sir. I'll just share my screen. Can you see my screen?
Yes.
Yes, we can see it.
Okay. So, hi, my name is Sharv. And today I'm going to be presenting my project on battery degradation using scientific machine learning. So, let me give you a bit of a background about who I am. So, I'm a high school student passionate about scientific machine learning and artificial intelligence. And over the past few years, I've cultivated a strong interest in the intersection of chemistry and AI, which has also led me to write my own research papers. So, a couple months ago, I had reached out to Dr. Sridath to learn more about scientific machine learning. I thought it was a really interesting concept, but I didn't think I would be able to handle these complicated concepts. However, their course was pretty nice, and being able to integrate theoretical science phenomenon into machine learning allowed me to further develop my interest in chemistry. And that's maybe the reason why I started to work on the battery degradation problem. And I also worked on it because of the interesting chemical processes behind it and the large scale impact it had in the sustainability field. So, under the guidance of Vizuara AI and the research program, mentorship program, my latest SIML my research work has been accepted at MIT's Undergraduate Research Technology Conference, and I'm really excited to share that I will be presenting that work the at MIT next month. And yeah, so let me tell you how it started. So I came to Vizuara AI research with recent knowledge about machine learning and coding. I almost had no knowledge about scientific machine learning and Julia and how to code in Julia, but I was really eager to learn new things. So I had started doing Udemy courses and developed a significant proficiency with the Python programming language and important machine learning techniques like neural networks and backpropagation. But I just had one problem, that there weren't many hands-on problems that I could apply my new knowledge to. So, as I said before, I had a passion about chemistry and sustainability, but there weren't many projects I could find on Kaggle or through Google that I could use to develop my passion and show people out there that I'm really serious about it, like, or stuff that I could solve as a beginner. So I started to look online and I found the Vishwara AI team, and their scientific machine learning course. So the scientific machine learning didn't mean much with me at first. And when I had reached out to Dr. Sridhar, after I looked into scientific machine learning, it was the exact thing I needed to develop my interest of applied machine learning and chemistry further. Um, applied machine learning to chemistry and sustainability further. But let me just recap a bit for what exactly is SciML. So again, SciML is a novel field that combines two ideas: science and machine learning. So in the scientific part, it uses equations and models based on laws of nature, like physics or chemistry, to understand how things work. Any field that has any type of ordinary or partial differential equations will have the capacity to run SciML frameworks, as Dr. Rajat had mentioned before. And machine learning, as many of you know, is a type of computer program that learns patterns from the data, helping us make predictions without needing exact rules for everything. So SciML brings these two together, and it uses the scientific knowledge we already have, like the chemical processes behind battery degradation, and and combines it with machine learning's ability to find patterns in large amounts of data. So this makes it better at predicting things like battery degradation just because it doesn't rely on past data, and it also understands how batteries work at a deeper scientific level through those ground truth equations. So you may ask why SciML is better than traditional machine learning. So traditional machine learning looks for patterns in data and makes predictions based on only on what it's seen before. Like, while this works in well in many cases, it struggles when there isn't enough data or the system being studied is very complex, like a battery, for example. So SciML is better because it combines machine learning with scientific knowledge. Instead of only relying on past data, SciML uses the rules and equations of science, like the chemistry and physics of how batteries work, and this will allows it to make more accurate predictions and forecasting, even with less data. It helps ensure the predictions make sense based on how the system really behaves instead of treating the entire problem as a black box. So, in short, SciML gives us the best of both worlds: the power of data and the reliability of science. SciML is one of the most powerful frameworks right now out there. And I know these terms might seem scary at first, but and to be extremely honest, when I started the SciML bootcamp with Vizuara, I didn't understand the mathematical aspect like solving ODEs and PDEs. But the whole team, Dr. Sridhar, Dr. Raj, and Dr. Rajat, they really helped me understand everything I needed to pursue my passion of applied machine learning to chemistry and sustainability. And I know many of you have scientific passions, but are scared or maybe confused on where to start. But my personal experience is that once we start to dive into the lectures that they have and start doing research and experiments on your own, it becomes extremely interesting and even satisfying when you get good results for yourself. So when it comes to scientific machine learning, there are some key areas of mathematics that are good to understand. Like, so let's brush through some concepts that I think that are good to have in order to learn scientific machine learning. So first, linear algebra. This includes understanding vectors and matrices, and these concepts are crucial for many machine learning algorithms and neural network architectures. For example, in neural networks, matrices are used to represent the weights, and understanding how to manipulate them helps in optimizing these models. So it's really helpful to have an understanding on linear algebra, but it's also not that necessary, but it's good to have in the sense that if you want to learn more about the theory behind things and really delve into these problems at a higher level, then I think these three tools are really helpful for you. Especially like calculus, for example, differential and integral calculus are fundamental when it comes to optimization problems. And optimization problems are the heart and soul of most training of neural networks. And calculus plays a big role in continuous models like even neural ODEs and UDEs, where we need to calculate changes over time in order to generate the lowest loss. And another important area is probability and statistics. So being familiar with distributions, expectations, Bayesian models, and statistical inference is useful for many machine learning models. And these concepts help us understand uncertainty, model validation, and how well our models are performing. Now let's focus on the most important area in SciML, which is differential equations. So in SciML, we work with systems of ODEs and PDEs, as it was previously discussed, and having a strong grasp of these concepts will help you model physical systems and understand how different parts of the system change over time. Yeah. So overall, having a solid foundation in these areas of math will make it much easier to understand and work with the algorithms used in scientific machine learning. So now let's talk about why I chose battery degradation as a problem and why it's such an important problem in today's date, especially. So as of 2024, carbon emissions have been rising at an exponential rate. And in 2000, the carbon emissions were at 25.5 billion metric tons. And this number has increased to 37.4 billion tons in 2023, as you can see in this graph. So this drastic rise has been a major concern for the entire world, and scientists all around the world were are looking for ways to mitigate climate change. So yeah, so therefore the usage of EVs and certain electric vehicles is pivotal to the societal transition towards a green future and sustainable energy systems. So as of today, EVs make around 18% of all vehicle sales globally, and it makes up an economy of a whopping $500.48 billion in 2023. And these EVs are useful in the sense that they're actively reducing at the rate at which carbon emissions are rising, and it's really helping sustainability. So now let's talk about batteries. So lithium-ion batteries, they play a central role to the performance and environmental impact of electric vehicles. However, battery degradation persists as a major setback, affecting the lifespan, efficiency, and overall sustainability of electric vehicles. So battery degradation refers to the permanent loss of a battery's ability to store charge, or a reduction in how quickly it can charge or release energy. So these issues are known as capacity loss and resistance rise, which are different ways in which a battery can degrade over time. So researchers are still finding ways to improve the design or materials of the battery or extend the capacity of the battery to make it last longer. But due to the scarcity of lithium and other metals, extending the capacity is currently very hard and somewhat expensive. So by monitoring and predicting battery degradation, we can optimize the life of the electric vehicle. So it's not only important, it's very important not only for the optimization of performance of the lithium-ion battery, but also to ensure that the economic viability and sustainability of electric vehicle technology is yeah so persists. So include it also helps us fulfill the United Nations 12 Sustainable Development Goal, which is ensuring sustainable consumption and production patterns. So we've discussed why battery degradation is such a major setback to the electric vehicle industry, but we need to know how to model it in order to predict it. So there are two types of battery degradation: calendar degradation and cycle degradation. So calendar degradation occurs over time, even if the battery is not in use. The capacity will eventually drain over time due to the internal aging mechanisms of the battery and the chemical reactions that occur within the battery. And cycle degradation occurs during use, during charge or discharge cycles. So basically, charge and discharge cycles refer to the process of a battery being charged and then discharged. So a cycle is completed when a battery goes from 100% down to 0% and then back to 100% again. So when the battery goes from 0 to 100, it's called a charging cycle, and when it goes from 100 to 0, it's called a discharge cycle. And over time, these repetitive cycles will cause wear on the battery, leading to faster degradation and a reduced ability of the battery to hold charge. So these two combine to express the cumulative degradation over time. And we can use this to calculate the state of health of a battery. which is a percentage that compares its current capacity to its initial capacity when it was new over a given time span. So, understanding the state of health of a battery is crucial for sustainability of electric vehicles. So, it enables users to optimize battery usage and maybe extend the lifespan of these batteries, reducing the need for frequent replacements. And it also aids in the conservation of lithium and cobalt and other scarce transition metals. And furthermore, understanding battery health supports recycling and second life applications. So therefore, we can kind of make out that this prediction of SOH is extremely useful, especially in today's age. So now that we have a bit of an idea of what battery degradation is and its different types, now we can discuss how to model it. So one such promising approach is scientific machine learning and its ordinary differential equations, which combines data-driven machine learning with physics-based models to accurately predict and forecast battery degradation over time. So in order to model and predict battery degradation over time, we have to use scientific machine learning and ordinary differential equations. So we will so calendar degradation and cycle degradation both have ordinary differential equations, as you can see, that can be calculated to that can be used to calculate the degradation over time, which we so these are equations that are base equations that are a standard, but in order to so each battery has a different set of differential equation. Like each battery will have a different set of constraints and it'll have a different molecular structure. So we needed to modify this equation so that it fits well with the electric vehicle we were testing on, which was a Nissan Leaf electric vehicle. And so we had to modify this to our own constraints. So when we take a look at this calendar degradation, we see some possibly unfamiliar terms. So for example, state of charge. It's pretty simple. It's just the battery percentage on your phone or laptop. For example, it just tells you how much charge is left. Like when your phone shows 100% when it's fully charged, and lower percentages as the battery gets used up and eventually goes to zero. And it's just like a fuel gauge on a car that shows how much gas is left in the tank. SOC shows how much charge is left in a battery, whether it's a phone, a laptop, or even an electric vehicle. And F is a piecewise function that uses the state of charge to calculate a separate value from the state of charge itself. So as we can see in this table, 0% has a corresponding value of 1500 and 10% is 2000 and so on. And this value helps us capture the chemistry, the internal chemistry behind battery degradation. As the state of charge alone, it doesn't help. It doesn't help much. So next we'll look at the time. So this is basically the amount of seconds that have passed since the battery was purchased or started to be used. And we can convert the years to seconds. And time is the only factor that contributes to calendar degradation. Now the next part is the exponent. So this part looks pretty intimidating to me and it's very confusing as well, but it's just an equation called the Arrhenius equation, which adds a temperature dependency. So it's basically a formula that helps us understand how fast a chemical reaction happens based on the temperature, which is TB in this case. And in simple terms, as the temperature gets higher, reactions happen faster. And the equation shows that when things get warmer, molecules move more quickly and they react with other molecules more easily. It's like when you heat water to cook something, higher heat makes the cooking go faster. It's just like that. And R and EA, these two terms over here, are the activation energy and gas constant, the gas constant and activation energy respectively. So EA represents the activation energy and R represents the gas constant. And the activation energy measures the minimum energy a reaction requires in order to be successful. If there's not enough energy, the reaction won't happen and the collisions won't be successful. So this was the outline of the ODE that we used for calendar degradation. Now discuss cycle degradation. Now this looks confusing, even more confusing than the first equation. But what I learned is, but when you learn what each of the terms are, it's pretty intuitive. So A, B, C, D, and E, they are all empirical constants with which means that it's for the specific type of battery that we got this paper from, they were testing on. This is basically empirical constants that help you fit to the model. And it's not very accurate because there's so many constants and there's different types of batteries that all have different values. So this is the amount of empirical constants is the reason why this equation is not so reliable. And now let's discuss the discharge current, or IB. So this is the amount of electrical current measured in amperes that flows out of the battery when it's powering a device. So it represents how fast the battery is supplying energy to the device. For example, if a battery is running a device that needs a lot of power, the discharge current will be higher. And the discharge current can affect how long the battery lasts. So higher currents may drain the battery faster than lower ones. So as we discussed earlier, there's lots of empirical constants, which makes it difficult to model battery degradation for other battery types as well. And so now that we have an understand of the differential equations representing calendar and cycle degradation, we can talk about cumulative degradation, which adds both calendar and cycle degradation to find the total degradation. And that can be used to find the state of health as we measured earlier. So if we take a look at these graphs, we see that as the temperature gets higher in calendar degradation, the degradation is also higher. This is because of the Arrhenius function that we discussed earlier. And as the temperature increases, the rate of reaction within the battery that causes battery degradation is higher, which leads to higher degradation and a lower state of health. As you can see in this graph, at 25 degrees Celsius, after 10 years, it becomes around 80%, but here in 10 at 10 degrees Celsius, it becomes around 88. So of course, this is a large difference. And yeah, so we can also see that cycle degradation does not contribute much to the end degradation. Like almost 1% or 10% or like 4%, sorry. And even when a car is driven for 50,000 kilometers per year, it is a maximum of 1% at 25 degrees Celsius, but 4 at 10% Celsius, 10 degrees Celsius. And this shows that it's kind of the opposite to calendar degradation, because as temperature decreases, the battery's efficiency drops, forcing it to work harder to provide the same amount of energy. So this increased strain leads to high degradation over time, despite the slower chemical reactions at lower temperatures. And the quadratic term involving TB, this one we saw, it takes the form of a quadratic form. Um, yeah, the quadratic term and the exponential function that includes both temperature and current over here we saw this exponential term. Yeah, so that reflects how temperature directly impacts degradation. So at lower temperatures, the battery operates less efficiency, and the exponential term could lead to higher degradation rates as the battery's internal processes struggle to maintain performance, resulting in faster wear and reduced lifespan. So that so now we'll discuss the SciML part of this, the more towards the machine learning part. So the first step of any SciML problem is to generate data. So the issue with this is that with this problem statement is that it takes too long for the battery to degrade, often 10 years to reach around 20% degradation, as we saw in these graphs. Yeah. So 10 years is a very long time, and it would take a lot of time and resources to conduct experiments for that long of a duration. Therefore, for this paper, we simulated the values from equations by adding both the calendar and cycle degradation, and then we integrated them using Julia, the programming language. And after this, we added noise of 0.25, which is basically adding random values to this data. This is without noise, and it looks like a smooth curve. But once we add noise, it looks a bit like raw, like a bit bumpy, and its random values are added at each point, so that we can generate synthetic data that might resemble real world data. And now let's start discussing the types of tools that can be used to solve this problem. So yeah, so this graph shows state of health without any noise, and this is synthetic ground truth data that we use to train our frameworks. And right now we are using the equations itself that I had outlined in the previous slide. However, we are working on an extended version where we found a data set to train on, and we're currently working that on that paper as an extended version of this one. And I'll be excited to share my work with you then as well. And this is also another really interesting part of research. And when we find a problem with a current approach or a hurdle, it's always nice to find ways to fix it or come around it and implement it nicely. And yeah. So now let's talk about UDEs. So UDEs are a type of equation used to model complex equation systems by combining traditional science with machine learning, as it was discussed by Dr. Raj and Rajat before. So, a regular differential equation uses known scientific rules to predict how things change over time, like how a battery degrades. Like when we see this is based on chemical laws. But however, sometimes we don't know all the rules perfectly, and that's where UDEs come in. They add a learning component to fill in the gaps where the science might be unclear. So UDs are like combining what we know with smart guessing to create more accurate models of how things behave. And we can replace any term or multiple terms with neural networks. For example, this calendar degradation, we chose to replace the square root of t term over here. If we this be The square root of t term was chosen to be a neural network because of it incorporates the time dependency of calendar degradation. If the UDE can capture the time dependency with precision, the SciML framework is truly powerful. And the only true challenge of UDEs is to determine which term should be replaced with a neural network to optimally recover the missing physics. When we do that, the next thing to do is determine the architecture of the neural network. For this work, we tried multiple neural network architectures and we found one that gave us the lowest loss. So 10 neurons was the input, and 5 was the middle layer, and 1 was the output. So for cycle degradation, this one, we replace the whole equation with the neural network. This is because there are 5 empirical constants. So ideally, we would want to replace each empirical constant with a neural network, but it became it became like overkill almost. The complexity became too much in terms of computation, and it took too long to train. But when the training ended, we got a very long loss. So that's why the cycle degradation term was replaced with a neural network due to the amounts of empirical constant it uses. And by that process, we are also removing the dependency on those constants. So when we put everything together, we can add these two, basically this equation with the neural network here and a full neural network that we can train on. And basically, this equation is then integrated um, over this time span from 0 to t, or where t is the time span of usage. And we can integrate it using Julia to find the end results. And to be honest, they were very good. So now let's discuss neural ODEs. So neural ODEs are a way to use machine learning models to learn how things change over time, similar to regular differential equations, but with a small twist. In simple terms, imagine a regular differential equation is a set of rules telling you how to do something, or telling you how something moves or evolves, like how a car speeds up or slow down, or how a battery degrades. So these neural ODEs will take this idea but allow a neural network to learn and adjust these rules from data. So this is basically when we add these two equations, we can replace we set that equal to a neural network and train it using that based on the ground rule equations. And instead of giving the system fixed rules, the neural network learns the best way to predict the changes over time, making neural ODEs very flexible. So in this, as I said earlier, we replace the whole equation with a neural network and let it find out the missing physics on its own. And we can fit the neural OD to experimental data or the ground truth data with the synthetic data we generated earlier. And this makes it extremely adaptable. So now I'll show you the end product of our efforts. So in order to show you the validity of our work, the most important part of any paper is, I think, the results section. And the aim of the UDE is to fit the ground truth data as accurately as possible. And the only way to quantify this is with loss. And in the end, after testing all the type of neural network architectures and going through hyperparameter tuning and training methods, we got a final loss of around 9.90 over 6 years compared to a very large loss in this. So as you can see in the figure, the UD prediction matches the synthetic data very well with minor discrepancies, if any. And this shows the ability and power of UDs to capture the internal dynamics of a complex system like a battery. So we tried lots of combinations, and most of the neural network architectures didn't work. But with the help of the whole team and their quick responses, they really helped me get through my obstacles. So as you can see in the slide, I went from two absolutely different graphs where this doesn't make much sense to a graph where it's very accurate and smooth. So this was another part of research that I really liked during the process. So now I'll tell you about, just reiterate my journey a bit. So in June 2024, I started with Vizuara. I reached out and I finished the SciML bootcamp, and I really recommend it because it's very useful in long term, as Dr. Raj and Dr. Rajat have already iterated. And I asked the Dr. Sridath and the Visual AI team about any possible problem statements related to sustainability and chemistry in general, because I'm very interested in chemistry. So we started the battery degradation problem, and I learned with I didn't have much experience on writing papers before. I only had done a few other papers before this, but I learned from their research paper writing course, and I started the experiments, and I got really good results. And I submitted to MIT URTC, and it's got accepted. So I'm really happy about that. So thank you for listening to my presentation, and I'll be happy to take any questions you guys have about battery degradation and any other things that you have questions about. So thank you.
Thank you, Sharv. Guys, you can ask any questions you have to Sharv in the chat. Meanwhile, I'll be in the last part. We'll take a few questions, but before that, let me talk a bit about the exact scientific machine learning bootcamp that Sharv was talking about. I hope you all can see the website. We'll put the link in the chat. So this is the landing page of the website. And by the way, amazing presentation, Sharv. I hope all of you are inspired by seeing his work. It is, we are not finishing the work just with the MIT URTC conference. It's of course an amazing conference, but we are also hoping the work could be submitted to NeurIPS and many other top machine learning conferences all over the world. It's of top-notch quality and it's one of its kind. So great work, Shav, and at such young age, it's a really an inspiration to all of us. So thank you so much for your awesome presentation. So this scientific machine learning bootcamp was started with exactly this goal in mind, like exactly what Sharp showed you today. We wanted to work with students or industry professionals. The students could come from high school background or undergraduate background, or they could be doing PhD, or they could be working in a company. Anyone, irrespective of their age, can they learn machine learning? And can they incorporate their personal interests? So Sher was interested in chemistry. So we were looking at a few other problem statements in the beginning, and then finally we stumbled upon the battery degradation problem. So similarly, is there something that really interests you, and can we incorporate ML into it? And can we bring out a tangible outcome at the end of the day so that you can present it in top tier conferences? So that was the goal. And what you just saw from Sher's presentation is exactly what we were supposed to do. So just go to this website, and this is a short 8-minute video in which Dr. Raj explains every single detail about the bootcamp, its duration. But I'll also explain it briefly right now. There are basically, if you scroll all the way down, there are 4 plans: researcher plan, student plan, community plan, and industry professional plan. So researcher plan was the one in which Shar was part of. It has one singular goal. It is to first teach you Julia, and then teach you the framework of scientific machine learning, like how to set up a given problem statement using UDEs or neural ODEs.
how to solve them, how to perform basic hyperparameter tuning so that you know what kind of, how many hidden layers you have to choose, what should be the learning rate and bunch of other hyperparameters. How do you do this? So this will be applicable whether you are working in SciML or traditional ML using Python. So this skill is highly transferable irrespective of what you're working on. And this will involve a few different types of material. One is pre-recorded videos. We have to do that because people are joining from different time zones at different points of time. So the videos are pre-recorded, but there are a few other material in the form of documents and very useful links. And at the end of that, after each module, you will find one assignment for you to submit. So one of the first assignments is literally installing Julia and writing the first Hello World code equivalent in Julia and submitting that. So similarly, each assignments are of progressive difficulty. And one of the last assignments is setting up a complex problem statement in universal differential equation format. And once you submit that without using ChatGPT or without, copying or finding the solution from somewhere on the internet and pasting it in the assignment, if you don't do that, if you solve it by yourself, you can be guaranteed that you will be pretty comfortable at setting up SciML problem statements. After that is where the research paper writing starts. And research paper writing, we have again divided into a bunch of assignments. And there are roughly 15 to 20 assignments starting from initially picking up the topic, writing the bullet pointed introduction section, then making the figures, and finally writing the paper, and then figuring out where to submit. So Sharv went through all of that process in the last 2 to 3 months to finally create this paper, which is currently accepted at MIT URTC. So that is the researcher plan. In the student plan, this one, the research paper writing part is not involved. It is completely passive plan. The researcher plan is very much active in the sense that we'll be constantly interacting with each other with respect to assignments or with respect to the paper writing. Student plan has no such thing. It is a pure self-paced passive course, which you can take anytime right now. And if you want later, you can upgrade to researcher plan. Community plan is something in between student plan and researcher plan, meaning it has all the assignments which we ourselves will be giving you assistance in terms of if you come across some difficulty in solving a particular assignment, we ourselves will be taking care of it and we'll help you with that. And plus we'll have a nice community of people who are working on the community plan who may want to later work on the research paper in the research plan. And industry professional plan is, as the name suggests, it's meant for industry professionals. But sometimes we have asked industry professionals to not take it and take a research plan first and then later upgrade. But basically, we have included some additional modules on transformers, generative AI, and large language models with the intention to help a few industry professionals who actively asked us, hey, can you include that as well? Because it will go very much hand in hand with what they want to accomplish. And most of these industry professionals want to accomplish one thing, like they don't want to become obsolete by not knowing the skills of machine learning, either in their own team or in the company in which they are planning to switch. So they would like to have the skill of ML in their arsenal, and especially they would also like to have the skill of generative AI, transformers, large language models in their arsenal. So we have included that as well. So researcher plan and industry professional plan are very much alike. Industry professional plan is the advanced version of researcher plan. Student plan and community plan is alike in many ways, but community plan is the more advanced version of student plan. We have a document which lists the entire curriculum of the SciML part of it. We have not included the curriculum of the research paper writing part of it. It's a separate thing. It will be probably 5 pages if I show it right now. But basically, at the end of these 15 modules, these 15 lectures, you will be set with Julia, UDE, SciML, and how to do hyperparameter tuning for certain problems. And if you go to we'll actually share this link in the chat. Just check this PDF. It has every single details about pricing, the duration. So the duration is actually for researcher plan, it's roughly 3.5 to 4 months. Actually, for us, Sharv is the person to graduate the fastest, and he finished, if I remember correctly, most of the assignments in SciML in 1 or 2 weeks. No one else has done it that fast. And research paper also he did pretty fast, and thanks to the MIT URTC deadline. But basically, the duration by default is like 3.5, 4 months. Most of the students end up doing that, but sometimes people have personal issues which might end up, extending the deadline further. And just have a look at this document. And the most important part of this document might be for you, it might be the last few pages in which we have listed a few set of projects. So let me check if battery degradation was part of this or not. I don't remember actually. I'm not sure if it, yeah, so battery degradation, I don't think it was part of this. We discussed it separately, right, Sharv? And
Actually,
Sharv,
sir, it was, I think, it was
it
a
was.
bit, I think so. If I'm not wrong, it's a
Mhm.
little in material science, yeah, it was
Yeah, I remember initially we were discussing these two problem statements, and then
Yeah.
later, yeah, it's here. Yeah. So then we thought we'll pick a battery degradation problem statement. Yeah. So basically, you can either pick a problem statement that is interesting for you from this list itself, like what Sharv did, or you can propose a problem statement which is not part of this. And this is like an expanding list, like as and when we think of good problem statements that are relatively unexplored, which will add value to literature, it will be very good. And all the things that are listed here are, in fact, extremely impactful problem statements. We are also currently working on a big mega project. So Dr. Rajat showed you about the SIR work, which Raj had done. So that SIR work was basically proposing a better model to predict the spread of COVID given certain conditions, right? And the original project was done for a few regions like US, China, India, etc. So now this mega project will be the biggest ever scientific machine learning project in the world, where we are planning to incorporate COVID data from almost all major regions in the world. So we are planning to have multiple co-first authors on that paper. And it will most likely be like a huge, maybe 40, 50 page research paper. So the work is just in the inception stages. We are still figuring out who should be working on that, because we want really motivated, talented people on this. Otherwise, there will be a lot of dilution of responsibility and things will not progress. But these are the things that we are envisioning. Like we are aiming for top tier conferences and top tier journals. And we hope that at least a good fraction of all these projects can end up in those places. And I also want to show you one more last thing, which is the way in which we work. So even when we were writing the paper with Sharv, we started with a similar, the paper we won't be showing right now because it's still in the press, in the sense that it's yet being reviewed, and it's being published after the MIT URTC conference. So we'll of course be sharing once the paper is out there. But basically, we'll be working in Overleaf. If you don't know how to write papers in Overleaf, don't worry, we can learn all of this. This is not a big deal. So we work with students and we comment on the papers directly within Overleaf. This thing is not loading for some reason. And this will ultimately help us take the papers into a really, really good stage. One more thing that we have started to do recently is for those papers that become those papers that get into a really, really good shape. We are also contributing technically and otherwise, so that we can add us also as second, third, or fourth authors, so that we can take the paper into an even better shape. And hopefully that will help us take the paper to better avenues, even top best tier conferences. We are also seeing if we can invite MIT professors like Dr. Chris or other big names in scientific machine learning to work with us in the paper. Like they can review it, they can add comments, and they can provide feedback or even contribute technically. And if they are interested, they can also be part of the paper. So we are thinking of such collaborations in SciML. It's definitely first of its kind, and I'm pretty sure many papers will reach good avenues. And maybe next year around this time, when you are listening to our webinar, probably you will see some of our papers actually out there. So this is overall the goal. If anyone did not understand the exact difference between the plan, or if you have any other doubts about the SciML Bootcamp itself, feel free to put it in the chat. We'll be answering right now. And if you have any other questions about Sharv's project or any other project, please put in the chat. We have another 9 minutes. We can try to answer any of your questions.
Yeah, I just want to share one document which explains some of the other research papers which have been published in this field, so that people in this call can actually relate to the fact that it's not just battery degradation, but several fields in which SciML papers have already been published. So I'm sharing this link in the chat. Please go to this link. So here I've opened some papers for you. This paper is in the field of civil engineering. It's a 36-page paper. But if you scroll down to it, hopefully after this webinar, you won't be scared by this paper, because as we demonstrated, there is usually an ordinary differential equation at the heart of every SciML paper. For this civil engineering paper, they are modeling beam dynamics, and this is the ordinary differential equation they are considering. And what they're essentially doing is that they're taking this equation and they're replacing some parts of this with a neural network. That's it. Similarly, here is another paper which is in the field of chemical reaction systems. So all of you who are biological engineers or chemical reaction engineers, just take a look at this equation. So if someone is scared of SciML or ML, they will think that it's a 30-page paper. How will I be able to understand this, right? But as we have learned here, always look for differential equations when you look for a SciML paper or when you read a SciML paper. So look at this. This is a set of 4 differential equations. And these researchers, they have simply replaced these terms with neural networks, and they have tried to recover the chemical reaction equations based on the data alone. Then here is another paper which is related to what Sharv worked on. This is Universal Battery Performance and Degradation Model for Electric Aircraft. Similar to the ODEs which Sharv showed you, here also if you scroll down below, you'll usually see this ordinary differential equation. So let me take you to that point. Yeah, see this set of ordinary differential equations. And here also what these researchers have done is that they have taken these ODEs and they have replaced parts of this with a neural network right over here. So I hope you have started to see some patterns. We want this webinar to be such that you appreciate what we taught you, but we also want you to know that whatever you have learned here can be applied to the project of your choice, to your own project. So we wanted to equip you with these skills also and not be afraid of this field of scientific ML. Also, if you have any doubts or questions and if you want to brainstorm regarding project topics for your field, you can feel free to email us at this email address which I've mentioned you here, which is hello@flywithesh.com. One last thing which I wanted to share is that many people have asked about ML transition resources, right? And I shared this document in the chat. I hope everyone has received this document. So we have prepared this document especially for students who want to transition to machine learning. So if you want to develop firm understanding of ML concepts, neural network concepts, go to this document and try to follow these resources. So these 3 resources are from our own YouTube channel, and probably some of the best in-depth ML videos you might learn. And then as you develop this understanding, take a look at the Scientific ML Bootcamp and some other links also which we have mentioned over here. So learning ML is a continuous process. Even all of us are learning every single day, but this resources document is probably a good way to have everything compiled. Okay, any other questions in the chat which we have not covered? Let's see. Julia language, right? Many students are asking why Julia? Like, what's so special about Julia? Um, Let me actually share my screen a bit to tell you what's so special about Julia. So if you go to this Julia lab, this is where I completed my PhD at MIT, and these were the founders of the Julia language itself. So I work very closely with these people, and I can very confidently say that if you go to this website, sciml.ai, this is the scientific machine learning ecosystem at Julia. And some of the packages which they have for physics informed neural networks, for UDEs, for neural ODEs, they are some of the fastest packages for scientific ML. Python is good for traditional ML like data analysis, computer vision, or NLP. But if you're looking at scientific ML, Julia is very fast. And it's also a beautiful language to learn, really. When I looked at Julia code, it looks elegant, it looks fast, and it looks simple to understand. So I did my entire PhD in the Julia language. And I really would encourage all of you, if you're transitioning to SciML, Julia is actually it's a really good language to get started with. It's very beginner friendly, I would say.
Yeah, many students might be wondering if they can fit SciML into their problem statement. Instead of thinking like that, it's better to see. So what is, are you looking at things like images or sounds or just data, which are just numerical representations, right? Image is just bunch of pixels, which are just numbers. Maybe an audio is like just its waveform, bunch of numbers. But instead of that, so first you have to think the problem statement that you're working on involves something like that, which is a collection of numbers, or is it more like a scientific phenomenon? And what is a scientific phenomenon? It's almost always there is a driving force and an opposing force, and the driving force may match the opposing force. In that case, there will be an equilibrium, and in that case, the rate of change of something with time will not be there. But if it is not in an equilibrium, there will be a difference, and that difference will cause something to change over time, which is why we have these differential equations. Sometimes things may not be described in terms of force. Sometimes it will be described in terms of energy. There might be an energy that is kind of driving the phenomenon, and there will be some energy dissipation which is causing the phenomenon to maybe not accelerate in an uncontrollable manner. So this applies to almost every field, like whether you are working in semiconductor, if you're designing chips, the way heat dissipates, it's a balance between the rate at which heat is generated at its source and the rate at which it's dissipated away. If this happens, if these two things are equal, the temperature distribution won't change like over time. But if the rate at which heat is being generated is greater than the rate at which it is being dissipated, the chip heats up. So this is true for pretty much any system. So if the system that you are looking at has something like this, where you can describe the phenomenon based on a driving and opposing force or driving and opposing energy, then that means that there is a scope for incorporating SciML into that. But you should not think like, oh, how can I incorporate SciML into my problem statement? There is no compulsion that you should incorporate SciML. But I would say if there are 100 people in this call, for 90 people, maybe there is a possibility for incorporating SciML. But if you are strictly working on maybe image classification or I don't know, image segmentation or something like that, probably SciML is not for you, at least for that problem statement. But you will encounter anyway some other problem statements in which you will naturally end up working on things which are described by physical dynamics. And of course, SciML will be very much useful for you. And sometimes you might be wondering like, okay, what if I don't find the data set? That happened with Sharv, right? So Sharv was explaining these battery degradation happens over 10 years of time, and it's often very difficult. So cycle degradation is easy to get because you can accelerate and decelerate the charging and discharge cycles. So cycle degradation over maybe 50,000 cycles or 200,000 cycles, you can get fast. You can do accelerated experiments. But how would you truly simulate calendar degradation? Because calendar degradation is simply happening over time. How do you accelerate 10 years, right? So there is always that problem that in some problem statements is impossible to get actual experimental data. In those cases, we can find ways in which, so in that case, then you will be wondering, if we create synthetic data, then what's the point? The point is that we create synthetic data and add noise. So as much as possible, we are mimicking a natural system, right? Which has noise. But the real point here is to show that, hey, it is possible. If you had experimental data, it is possible for us to forecast beyond 10 years. We can forecast for you with high degree of accuracy. And then they will ask, but how are you able to say that? We are able to say that because, see, we have already done that for this synthetic data with noise. So nothing prevents us from forecasting it. If you had data for 8 years, we can forecast it for 10th year, 11th year. So that's the idea. So here, essentially, you are showing a proof of concept for the first time to someone in the field of, let's say, electric vehicle, lithium-ion battery. Let's say there is a person whose job is to predict or kind of analyze the lithium-ion battery. you can give that person a proof for the first time that, hey, here is a better model than using 15 different empirical constants. Here is a better model. Like here we can forecast and also predict, train a model and forecast for a time which you are not familiar with. You don't know what will happen after 15 years. Hey, here is our model. It's working with 99.9% correlation with time until 8 years. So we can predict for the next 7 years as well. So you give that proof of concept for the first time, and then that opens a door to a completely new area of research. So once Sharv's paper get published, it opens a new area basically. Then a lot of papers will follow up. They will try to do something else, some additional delta things. But the first person to do this will always get all the accolades. So if you are one of the first persons to incorporate SciML and show the proof of concept that in this biological system, I show for the first time that SciML can be incorporated. Recently, there was a paper which was about nuclear fusion reactor. Raj, do you have the link to that paper? It'll be nice to show. Basically, it was in NeurIPS only last, I think, 2023. If you look at the paper, it's extremely simple. You might wonder that, oh, nuclear fusion is such a big thing. No, the differential equation that they are looking at is super simple. And you will wonder, if you had those equations in your hand, you would have also published in NeurIPS. But the reason why that group from MIT, they ended up publishing in NeurIPS is because they did it for the first time. For the first time, they showed that I think they're modeling the plasma or something. They can do it using SciML. So I think all of you have scope to do something like that in your respective field.
Yeah, I think just found it.
Yeah.
There's one more paper.
Yeah, there was one which had I remember the kind of graph they had, like loss function or something in the last plot.
This is the one. Can you check the second one?
Yeah.
That's the one.
So yeah, so this is the paper. Just look at their equation. That's it. These three equations form their model, and so it's so simple. This is probably one of the easiest differential equations that you will ever see. And then just have a look at what they're plotting. They're just plotting the training and validation loss for the models that they have. And just look at where this is published. This is published in NeurIPS 2023, right? Yeah, this was at the NeurIPS workshop 2023. So it's because they are one of the first people to show this. So this is by no means making nuclear fusion reactor better right now, but it opens a door to that for the future. So you can also do the same. But I think we are over time right now. It's been great, and thank you so much, Sharv. It was wonderful to listen to your talk, and it's really inspiring for all. Although we know your work really well, it's still inspiring to see your talk. And we'll be.
Thank you for the opportunity. Yeah.
Yeah, no problem. We'll be conducting another SciML webinar, of course, with Sharv after his MIT conference is done. So at that time, he'll show the full paper and the entire simulation, everything. We'll most likely have our next scientific machine learning webinar sometime end of this month, right? Mostly after 30th of September. So see you all at that time.
We'll probably
yeah, guys, can we take a photo of all of us probably doing a thumbs up or something? So this has become now customary for our webinars. We started doing it 3-4 webinars back, and now we are doing it at the end of every webinar.
Yeah, don't be shy. Just one photo.
Just do a thumbs up so that we can click a screenshot.
Okay.
Okay, everyone. Thanks a lot.
Thank you, guys.
Thanks, guys.
Thank you.
Yeah.
Bye.
Bye.